So we've now kind of gotten through the like K6 version of finite fields. We're going to step now into the Algebra 2 version of finite fields. So what do we try to do in Algebra 2? We typically try to solve equations. This might be more of an Algebra 1 equation, but here's something that we might wonder, is there an x that satisfies this equation? And we try to graph equations. These are, I think, the two things that students in Algebra 2 spend most of their time on, is solving equations and graphing equations. And we might wonder, does it make sense to do Algebra 2 over finite fields? Can we solve that equation, and can we graph this equation? And it turns out the answer is, yeah, we can definitely graph equations over finite fields. And sometimes we can solve equations over finite fields. In particular, the first equation that I have up there does have a solution. X equals 1 satisfies that first equation. But the second equation that I have up there, x squared equals 3, you're not going to find any solution, at least within this field, to that equation. So we'll talk a little bit more about that second equation, x squared equals 3, in a moment. But I wanted to just sort of give it some visual context for thinking about finite fields and graphing with finite fields. The basic way that students are taught to graph equations, at least in the really elementary context, is just plug in some points. If you plug in x equals 0, what do you get? If you plug in x equals 1, what do you get? If you plug in x equals 2, what do you get? There's certainly nothing stopping me from plugging in points and then plotting the points on some sort of grid. And here I have the 5 values that I could possibly plug in for x and their associated points on the graph. We might wonder, how does this compare to our sort of usual graph of 4x plus 3? Here's what our usual graph of 4x plus 3 would look like. It has slope 4. It crosses the y-axis at y equals 3. And you can think about the graph on the finite field as just sort of wrapping around. Whenever we cross 5, you sort of imagine we're playing Pac-Man, and you come out on the other side of the board back at 0. So this blue part is just a continuation of that red line, but wrapped around. So we're sort of graphing on a cylinder, it seems. Here's the sort of next few wraparounds. And in fact, this wrapping around matches up along the edge on the right and the edge on the left as well. So this really is we're graphing on a Pac-Man board. More technically, you could say we're graphing on a torus or a donut, meaning we sort of take our plane and we wrap around the top and the bottom to meet, and we wrap around the left and the right to meet, and we somehow turn our piece of paper into a donut. So equations in regular life, we graph on a flat plane. Equations on a finite field are sort of looped around with respect to the x-axis and looped around with respect to the y-axis. But we can still ask the same sorts of questions we usually can. We can ask, does it cross the x-axis? Does it have roots? So let me pause at this point and invite questions, because this is sort of a weird and abstract part to some degree. Does it feel clear? Any?
There's a hand up.
Oh, there is.
Yeah, so you said x equals to 1 works for 4x plus 3 equals to 2. Can you explain that, please?
Yeah, sure. So if I plug in x equals 1, then I get 4 times 1, which is 4. And then I add 3. And on this clock, 4 plus 3, if I start here and count around 1, 2, 3, then it works.
Yeah, I wasn't seeing it in as modular arithmetic. I just thought it was normal. Yeah, thank you. That makes sense.
Gotcha. Yeah, I I'm being a little bit loose here with my use of equal signs and the just like not visually overwhelming the slides. I've made some choices to sweep some stuff under the rug. So yeah, for the rest of the conversation, we're going to be focused on the field of order 5. So all the equal signs are focused in that field. And I'll comment, you could actually solve this equation here in the sort of usual way of subtract 3 from both sides and then divide by 4 is a totally valid way to do algebra in this field. Any other questions at the moment?
I have one question.
Yeah.
Seeing this graph, does this imply that this finite field can have not only integer but some real numbers?
Yeah, you make a really good question. That's a really good question. No. So the lines here are more for giving an intuition here than for actually indicating that all of the points in between are actually, they don't exist. They're not there. So the relationship between these graphs is sort of, if you took the usual graph and then wrapped it around and then deleted everything in between the grid points.
Oh, okay, I got it. Thank you.
So yeah, this point here that's shown as like, it looks like there's a point here at 1/2, comma 0, like 1/2. Yeah, there's some fuzziness that I'm sort of trying to paint broad strokes in order to connect some intuitions that I am sort of, there's some imprecisions here, and I'm glad you pointed that out.